In the first video on stochastic processes, we looked at what those processes are, and we discovered that they are systems that evolve over time with randomness, with uncertainty, right? And we contrasted stochastic processes, which are, we contrasted stochastic processes with deterministic systems, which are fixed over time as far with the same initial condition, you get the same results all the time. But for stochastic processes, the trajectory of the system is always probabilistic because it keeps changing as you keep running the system. So in this video, looking at elements of stochastic processes, which we started considering already in the first video. So let's go into some depth looking at elements of stochastic processes. So a stochastic process, of course, is a collection of random variables indexed by time or another parameter. So it could be time, it could be whatever else you're looking at. So you have x of t such that t belongs to time, where t is the index, all right, usually time, and x of t is the random variable itself, and t is the index set, all the times available to the system. That's what the index set would mean. The examples of probabilistic process include stock prices evolving over time, daily temperature measurement, queue length in a service system, population growth, Brownian motion. To understand stochastic processes, we study five fundamental components. We have the probability space, the random variables, index set of time, then state space and sample paths. So in essence, these are the elements we are considering: probability space, random variables, index set, and state space and sample paths. So let's start with the probability space. So a probability space provides the mathematical framework for randomness. It is defined as a triple, and the triple, that's the triple of omega, F, and P. So omega is the sample space, that's all possible outcomes. Then F is the sigma algebra of events, and P is the probability measure. So this structure allows us to assign probabilities to events in a mathematically consistent way. So example, right? If we toss a single coin, so suppose we toss a coin, the sample space is simply this. So this, of course, the sample space talks about all possible outcomes. When you toss a coin, there are only two outcomes, H and T. So the head can show or the tail can show. That is the omega, the sample space. Then F is the sigma algebra of events. That's your event space now. So your event space F now will be, what are the possibilities? When you toss a coin, uh you can have head, you can have tail. Okay. I think the deal is, what are all the possible, you have the sample space is H and T. What are all the possibilities of this? So of this set, you have the empty set, which is a subset of the H and T. You have H, which is a subset of H and T, T, which is also a subset of H and T, or omega itself. So these are the event space you can have right here. So then you now have the probability measure. Probability that a head will show up is 0.5, and probability that tail will show is 0.5. So this simple experiment forms a probability space like this. So this is what you mean by the probability space. So you talk about the sample space, the sigma algebra of events. We are going to look more into the idea of sigma algebra of events and then probability measure. Now, what about you have an infinite coin tosses? So in stochastic processes, we often consider repeated experiments. So if you toss a coin 1 million times, so it is considered as, or you toss it even maybe not up to 1 million times, like you toss a coin even 100 times or something. So in stochastic processes, we often consider repeated experiments. Example sample space in that case would be omega, which is h comma t raise head and tail infinite times. An element of this space might look like HTT, HHTTT, and it keeps going on and on. So it's more like you toss a coin 100 times and you take note of what you get each time. So each infinite sequence represents a possible outcome of the experiment. This structure is commonly used in random walks, Markov chains, and Bernoulli processes. Now, so we have looked at the first element, talking about probability space. So we are moving on to random variables. Now, we are talking about elements of stochastic processes. So we have taken care of probability space. Now we are moving to talk about random variables. So for random variables now, we say that a random variable is a function that assigns a numerical value to each outcome. Okay, a random variable assigns a numerical outcome to a numerical variable value rather to each outcome. For instance, you have your variable x, it assigns the omega to the set of real numbers. So for every outcome omega belonging to omega, the random small omega and big omega, right? The random variable produces a number x of omega, right? So let's look at a dice roll. So for a dice roll, for instance, so the sample space is 1, 2, 3, 4, 5, and 6, right? So if you define a particular random variable, say x of omega will be the value of the dice. For instance, the outcome omega compared to the value of the dice. So if you have one, right, one can only appear one time. So for two, the value is two. For six, the value is six for a dice roll. Okay. So now indicator random variable. Now, so to talk about the indicator random variable, um, if you define x of omega to be 1 if head and 0 if tail, is in this case now you call this kind of thing a Bernoulli random variable. So you have only two possible outcomes. You say that is a Bernoulli random variable, and that can be represented using a Python simple Python code. Here we are simulating 10 coin tosses. So tosses, so of course it's random, right? So 10 coin tosses, and you convert to indicator random variable. Either H is 1 or otherwise it's 0. So you have the outcomes here. So you have outcomes H, T, T, H, T, 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 T. And then the random variables, that's head is 1, tail, two tails, 0, 0. Head is another one. All the rest are tails, 0. So if I run it again, it's going to give another set of results entirely because it's a random, it's a stochastic process. Okay. So now you see, tail comes first, you have head, you only have, there are only two heads in this case. So if I run it again, you have like 1, 2, 3, 4, 5, 6 heads in this Euclid. Okay, so it keeps going like that. That's like your Bernoulli random variable. Okay. Now, so we've talked about the probability space, we've talked about random variables. Now we want to talk about the indexed set, or what you call the time. So a stochastic process is a family of random variables indexed by time, right? So at time one, time two, time three, and things like that, you have a particular value of the random variable. So the index set T determines how time is modeled. So whatever T is determines how time is modeled. So you have types of index sets, like you have discrete time, that's countable time. And that's possible. Maybe you're doing an experiment, and every minute or every hour or every day you want to take a kind of recording. It's just say, okay, so you take at time 0, that's the initial condition. So after one day, if you are following day, or if it's after 1 minute or after 1 hour, you record. After another 1 hour, you keep recording that. That's discrete. But then, so examples of that would be things like maybe daily stock price. So what is the price of stock today, or exchange rate? What is it today? That's daily. Then you have number of customers arriving per time, and you have random walks too. Then you have the continuous time. Continuous time is, I mean, it just keeps going on. So you can get into the system at any point in time and find out what's happening. So you have that in like Brownian motion. Of course, Brownian motion, we talk about that with respect to chemical reactions, right? So you just have all the molecules moving all around, all over the place, right? So then you have diffusion processes and continuous time finance models. So in this case now, we have example of stock in stock prices. So let x of t be stock price at day t. Then the stochastic process is x naught. That's the initial time. Then after day 1, day 2, day 3, and so on and so forth. That's for stock prices, and we can model that here. So if you take t to be 10, maybe you're looking at 10 days, you want to generate random values representing a simple time series. So you have x now because you have that randomness. So random is the key thing here, and it is normally distributed. Okay. So with mean 0 and standard deviation 1 or something like that with that time. So if you print x, so you see what you have for a particular set. If you run it again, these values are going to change. Okay, you run it again, they keep changing and changing because it's a stochastic thing you're dealing with. Now we talk about state space. So we've talked about we've talked about probability space, random variables, index set, and now we're talking about state space. The state space is the set of possible values that the process can take. So you have S is the collection of possible values of x of t. So types of state space can also be discrete state spaces, where you have Q length, like S 0, 1, 2, 3, and so on. Then yes, you can also have continuous state space like temperature, which is just which keeps going from minus infinity to infinity. So an example would be a weather model for state space here. For a weather model, state space can be any of sunny, rainy, or cloudy. You have those three discrete points. So this type of state space is often used in Markov chain models. Like, okay, what is probability that if today is sunny, tomorrow is going to be rainy, and what is probability that if tomorrow is rainy, the day after is going to be cloudy. So that's more like a Markov chain kind of thing as you're going to see as we move on. Then talking about random walk now, so the state space S is an integer. So because you can move from this fixed point to another fixed point and keep moving around like that. So possible positions that you have like all the integers -2, -1, 0, 1, 2. By the way, 0 is an integer for sure. So imagine now that we are doing a random walk from, say, of course, we already saw, I think it was in the last video or so that we saw random walk that it happens from -1 to 1, so it can keep moving around. So if you have 20 moves to make like that, so maybe you have -1, -2, -3, -2, and just keeps going like that. So if I run it again, of course, it's going to keep shifting. It's going to keep changing in values like that. So that's the idea of random walk right there. Then finally, we have the fifth element. The fifth element is sample path. So a sample path, also called a realization, is one possible evolution of the stochastic process. So for a fixed outcome omega, x of t of omega as t varies, right? So for a fixed outcome omega, x of t omega, okay, I think there's something, okay, yeah, for this fixed outcome. So you have that as t varies. So each outcome in the probability space generates a different trajectory of the process. Okay, that's talking about the sample path. So example of stock price path now. Imagine the sample path might look like this. So at the initial time, the price of the stock is 100. After one time step, you have 102. After two time steps, another one time step, you have 101. At 3, you have 105. At 4, you have 103. And it just keeps going like that. So another realization would produce a different path entirely. Okay. So like what we have here. So you have a sample path of random walk. And like you already know, if I keep running this, it keeps giving different results, different paths. So you see, so that's why it's probabilistic, it's based on chance. So stochastic process is all about chance. Now we move on to putting everything together, right? We've seen the five elements of a stochastic process. We saw probability space, we saw random variables, we saw index set, we saw is the sample, the last one was sample path that we saw, and before that we saw state space. Okay, so those are the five elements of a stochastic process. So if you put everything together, consider a random walk, x of t, which is the summation from I equals 1 to t of yi, where yi, of course, this is clearly a random walk. Yi is 1 with probability 0.5 and -1 with probability 0.5. So elements of the stochastic process, you have them summarized here. You have the probability space can be like coin toss outcomes, random variable, that's step yi now, that's your random variable step yi. But your index set is time t, I equals 1 to t, that's t 0, 1, 2, and so on. And because we are using summation here, so it has to be discrete like that. Then you have the state space, which is a set of integers. And then you have sample path, which is trajectory of positions like that. So that's us putting the whole idea together of the elements of a probability of a stochastic process. Now let's quickly talk about Poisson process, which we've talked about before in the previous video. So another important stochastic process is the Poisson process. Let n of t be the number of events by time t. So example events, say phone calls arriving at a call center, radioactive decay, arrivals in a queue. So for this process, for instance, the probability space will be all possible arrival sequences, and random variable is like n of t. Index set is t, which is greater than or equal to 0, and you have state space 0, 1, 2, 3, and so on. And you have the sample path, which is the step function increasing over time. So this brings us to our practice problems again. So we have the following. Solve the following problems related to probability spaces, random variables, index sets, state spaces, and sample paths. Define the probability space this for a single roll of a fair six-sided die. Of course, the sample space this one now will be um we are talking about a single roll of a fair six-sided die. I guess I want to write that out, right? So here now we have we have omega F and P for a fair six-sided die, right? So now we need to understand what each component stands for from the previous thing we had seen, right? So let's go to that and look at it. So here now, okay, yeah. So we have this for a coin toss. So omega is the sample space. So omega being the sample space, what do we have? So omega is the sample space. So we have omega, that's the sample space. So for a six-sided die, that means you have one, two, three, four, five, six. Because it is fair, though, if it is unfair, maybe three is the winning number. Somebody might have tampered with four and made it three. Somebody might have tampered with six and made it three. That would be unfair, right? But if you have a fair die, you have one, two, three, four, five, six. So this is the sample space now. This is the sample space. Okay, so the next thing is F. That is the sigma algebra of events. That is the collection of all possible events. So you have the event space. So sample space omega, the event space, that's the sigma algebra of events. So that's the event space F now. So that's going to be a lot. I hope I can write everything. Let me see how far I can go because we have six events there. So for F now, this is the sample space we've done already. So now we have the um event space, event space F. So for the event space F, what do we have? For the event space F, we have, so I'll go as much as I can go and stop at some point. So we can have the empty set where nothing is there. Then you can have the ones, one, two, three, four, five, six. Then you can have them in twos now. You can have one, two. That's going to be a lot for sure. You can have one, two. You can have one, three. Okay. You can have one, four. You can have one, five. You can have one, six. You can have, okay, no. Yeah, there's no point doing this. I think we don't have, it's not this serious. Yeah, sorry. I think that was my fault. Yeah, it's not two coins. It's just a single coin. Sorry. We don't need all this. Sorry, sorry, sorry. Yeah, so it's not that serious. Yeah. So yeah. It's a single coin. I was already going to beginning to talk about two coins. Okay, yeah. So we should just have something like this too. Like this exactly. Yeah, sorry. So will be the event space F rather would be the empty set, and then you have one, two, three, four, five, six, and then the sample space itself. That's the omega itself. That's what we have for the event space. And then lastly, we have the P. That's the probability space, I believe. So the probability measure, okay? Probability measure. So for the probability measure now, that's straightforward because we have six things, right? So for the probability measure, okay, I guess I want to change this now. For the probability measure, P, for the probability measure, so what do we have? So we have P of 1. P of 1 will be 1 over 6. P of 2 is 1 over 6. P of 3 is 1 over 6. 1 over 6 because there are six possibilities. What's the probability that when you roll the die, you get one? That's 1 out of 6 possibilities. So each one has an equal probability of 1/6. So probability of 4 is also 1/6. Probability of 5, 1/6. Probability of 6 is also 1/6, basically. So that's how that goes for the for that question. So that's this simple experiment forms, so the whole thing forms a probability space like that. So for a probability space, you need the event space, the sample space, the event space, and the probability measure. So let's look at another question. Let's look at other questions and just breeze through them as much as we can. So a coin is tossed 3 times. Write the sample space omega. How many outcomes are possible? So a coin is tossed 3 times. Write the sample space omega, right? So if a coin is tossed 3 times, for a coin tossed 3 times, so the sample space, the sample space omega would be things like this. So for a coin tossed 3 times now, I think there's a way Mr. Monroe taught me back in Badai Grammar School, right? You have, so for a coin toss 3 times, so you know a coin has head and tail, right? So for a coin toss 3 times, the sample space would be something like this. You have, so um so the possible results, right? If you toss it 3 times, uh okay, what I'm just going to do is, first of all, you need to know that a coin has 2 faces because it's tossed 3 times, the number of outcomes. Maybe I should write that out. I think it is important. For a coin tossed 3 times, the sample space is based on is is based on the number of outcomes, is based on the number of possible outcomes, number of possible outcomes. Okay, let me check to see if I'm not mixing that up already to answer the second question. Okay. Yeah, I think I'm in order. So because the other question is how many outcomes are possible? So maybe I'll answer the second question first, which is okay, the possible number of possible outcomes, number of possible outcomes given by uh face f- okay, coin face coin faces, that's the number of coin faces raised to power the uh number of tosses. So that's simply a coin has 2 faces, tosses here. So that's 8 outcomes. So we're expecting 8 outcomes. And for those outcomes, uh the sample space, sample space, the sample space can then be given as what I was taught back then, right? You have omega, that's so because it's 8, right? Right head 4 times. 1, 2, 3, 4. Right tail 4 times. 1, 2, 3, 4. Then apart from that, you now write head. So you've written 4, 4. Now write them in twos. Head, head, tail, tail, head, head, tail, tail. Then finally, you write it head, tail, head, tail, head, tail, head, tail, head, tail. So these are the possible outcomes. This is the whole sample space. So you can have head, tail, head, tail, head, tail, head, and tail, tail. Basically. So that's how that's the possibility you have right there. Okay. So number 3, define a random variable x that represents the number of heads obtained when a coin is tossed 3 times. Okay, interestingly, we can just follow where I stopped the other time. I can just continue. It's the same question. Write a random variable x that represent the number of heads obtained when a coin is tossed 3 times. So number of heads obtained. Okay. So when a coin is tossed 3 times, so we can have hmm, how do I put this now? So is it like you have X mm, trying to see. I need to be able to situate this properly. List the values X of omega for all outcomes. Represent the number of heads obtained when a coin is touched 3 times. Okay. The values. I'm trying to think about this. So, well, okay, the random variable should be something like this. So, the random variable, the number of heads you can ever have will be 0. You can have 0 head as you have here. You can have 1 head as you have like 1, 2, yeah, 3. You can have 2 heads as you have here and other places. You can have 3 heads and that's all. So these are the random variables now. Okay. So I think the question is now asking, uh, list the values of x of omega for all outcomes. So what did you see as x of omega before now? I think there's something we did about x of omega somewhere. X of omega. So I'm actually thinking this should be some probability thing. So value of the dice. Okay, yeah, I think that makes sense still. Um, for x of omega now, so for x of omega, we have, so when you have 0 heads, okay, maybe I can make it into a table. So you have x and then x of omega. So for 0 head, okay, for 0 head, x of omega should be 1. That's the value, okay? For 1 head, so in how many places do we have 1 head? So this is 1, 2, 3. Yeah, we have 3 for 1 head. What about 2 heads? So for 2 heads, we have for 2 heads. Okay, let me make it this way. For 2 heads, we have 1, 2, 1, 2, 3. So for 2 heads, that's also 3. And finally, for 3 heads, 3 heads is only 3 heads is 1, 2. Okay, that's 1. So yeah, so this is the kind of thing we have in that situation now. So 0 head appears 1 time here, then 1 head appears 3 times, 2 heads appears 3 times, appear 3 times, and 3 heads appear 1 time. So that's the kind of dealing we have with that. All right. So yeah, so back here. All right. Consider the process x of t equals t squared plus z, where z is a random variable, taking values -1 to 2 with equal probability. What's the index set? What's the state space and all that? Yeah, you can check that out. Explain the difference between random variable and stochastic process. Yeah, we've discussed that. So please look at the rest of the questions. We'll go deeper and deeper into some of these things. So excuse me, any question that feels out of place right now, just don't bother. We are going to deal with everything step by step as we move on. So don't forget to try your hands on the questions. Um, you know, and let's see how well you understand these concepts. So on this note, I come to the end of this interesting video. Let me know how helpful this is for you. And if there's something that you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for doing that. If you haven't subscribed, why not go ahead right now, subscribe, hit the notification bell so you can always get alerted each time a new video is released. You can also click on join to become a member of the channel. All right, that gives you the opportunity to see some videos first before other people, or to even see some videos that others don't get to see because you're a member of the channel. We can hang out together to discuss whatever interests you on this channel. You can also request for PDF copies of my notes as a member of the channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.